the thunder of powerful engines echoing in the desert air. A plume of steam billowing towards the sky. Sparks flying from electrical wires. The blast from a controlled explosion. These sights and sounds belong to one of the world's finest state-of-the-art facilities for propulsion and materials testing. In the desert northeast of Las Cruces, New Mexico, NASA's White Sands Test Facility stands ready to challenge the safety and reliability of items slated for spaceflight. The goal at White Sands is to minimize flight risks. Safety, no matter what, is the first concern. From rocket engines to film for a camera, everything flown on a manned spacecraft has to be tested. Carefully controlled test parameters determine the strengths and weaknesses in hardware concepts and designs. This testing is crucial to mission success. Taking the risk here on Earth first will help avoid having to solve a problem miles away from home in the unforgiving space environment. As part of NASA's Johnson Space Center, the White Sands Test Facility is primarily a support organization. The testing requirements for the Johnson Space Center are the first priority for this facility. However, it also supports other NASA centers, various government agencies, and aerospace-related commercial industries on a reimbursable basis. The client provides the test article and defines the technical and schedule requirements.
And that is not part of the TRR.
White Sands personnel develop and conduct the test program to satisfy those requirements. NASA's White Sands Test Facility employs a team of over 700 civil servants and contractors. This self-sufficient facility includes an administrative area, 2 propulsion test areas, and a laboratories area. The moderate weather, arid climate, and remote location make this an ideal site for propulsion and hazardous material testing. Built in 1964, facilities here can test the entire propulsion system at one time to see how the components interact. While the larger Saturn V engines, which pushed the Apollo spacecraft off the launch pad, were tested at another NASA facility, the White Sands facility began its propulsion work with the development and certification testing of Apollo's service module and lunar module engines. These engines were crucial to the success of the Apollo missions. The service module engine put the astronauts into lunar orbit. Then the lunar module descent engine landed them on the moon. The lunar module ascent engine blasted them off the moon and back into lunar orbit. And the service module engine brought them back home. 4 dozen tiny reaction control engines on the lunar module and command service module steered the vehicles through space. Over the years, White Sands has tested more than 300 engines in over 2.1 million firings. Each test is conducted to make sure that the engines are safe and reliable. In the early 1970s, White Sands began tests for the shuttle's on-orbit propulsion systems, including the orbital maneuvering system and the reaction control system. 3 high-fidelity flight-like test articles were used for the development and qualification of these systems. Recently, these test articles entered a new phase of testing. In order to identify the life cycle limitations of the shuttle propulsion systems, NASA has developed the Fleet Leader Test Program. As part of this program, White Sands will periodically operate the test articles to see how repeated firings affect the system. These test articles will undergo more firings and checkouts than any of the corresponding flight systems. As a result, shuttle component problems resulting from long-term exposure to corrosive rocket propellants and multi-mission operation can be resolved before problems occur on flight vehicles. Propulsion testing is conducted in two separate locations, designated the 300 and 400 test areas. In the 300 test area, two test stands operate at normal or ambient atmospheric pressure. These stands are hinged to accommodate rocket systems which must be tested in both horizontal and vertical orientations, such as the steering thrusters which control the shuttle's position in orbit. A third test chamber allows rocket engine tests to be conducted under simulated space vacuum conditions. The largest of these, Test Stand 302, was extended to a height of 58 feet during the Viking Mars lander program in the early 1970s. At that time, it was used to simulate the physical and biological effects of a rocket engine landing on Martian soil. This work led to improvements to the rocket engine and its fuel prior to the launch of the Viking probe. The stand has since been modified to accommodate vacuum testing of space station propulsion systems. One of the largest instant steam generating systems in the country is located in the 400 test area. It can generate over 750,000 horsepower, which would equal the power of over 5,000 automobile engines. This steam generator closely simulates the space environment by allowing the interior of the altitude chambers to remain in a near vacuum during an engine firing. To create the vacuum, the engine fires into a large, specially shaped duct, which vents to the outside. Inside the duct are nozzles that inject cooling water and shoot high-pressure steam in the same direction as the exhaust is traveling. The steam is accelerated to supersonic speeds as it is ejected by the system. This creates a low pressure which has enough suction to pull all the atmosphere and the rocket's exhaust out of the enclosed stand. As a result, the engine and exhaust plume are kept in a near vacuum. Testing under vacuum conditions is vital because rocket engines perform significantly better in space than in tests at atmospheric pressure. This difference in performance must be measured precisely. Test stands 401 and 403 are altitude chambers used for testing liquid propellant engines. A full-scale shuttle orbital maneuvering system pod and a flight-type orbital maneuvering engine are installed in Test Stand Fleet Leader tests. Another specialized vacuum test stand, designated 405, was designed to determine the performance of the solid rocket motors typically used to boost spacecraft into orbits higher than the shuttle can reach. Solid rocket motor testing is difficult because these motors are often spun as they are fired. A special fixture was set up to spin the motors at rates up to 125 revolutions per minute. Motor pressures, temperatures, and thrust outputs are measured to verify compliance with performance guidelines. This stand can also test liquid-fueled rocket engines, such as the shuttle's steering thrusters. Each test stand is operated from the blast-resistant control center. Underground tunnels connect the stands with the control center and protect the electrical and instrumentation wiring. Each test article is instrumented with hundreds of devices which measure pressures, temperatures, vibrations, and flow rates. The test procedure is precisely controlled to allow a comprehensive analysis of the results. 4 sets of computers acquire and process the test data. These computers offer real-time test control plus digital and color graphic data displays. Engineers analyze the data to determine if the system met performance objectives. Following a firing, the propulsion system is carefully checked out and examined for damage. Propulsion testing is more than just fire and smoke. Often, White Sands personnel must develop procedures for safely handling toxic or hazardous propellants in various situations, such as loading propellants onto the shuttle. Other work involves continued development of environmentally safe systems for destroying toxic fuel waste products. Techniques are also developed for cleaning and refurbishing shuttle propellant components, which have accumulated contamination during more than 10 years of flight operations. Many special projects at White Sands are supported by an extensive laboratory complex. The laboratories area has 9 remote test cells designed for high-pressure testing with gaseous and liquid oxygen. There are also 14 remote test cells capable of withstanding explosions and designed for operation with hazardous toxic fluids. In this area, special equipment is used to examine the ignition, combustion, and explosive properties of typical spacecraft materials and propellants. White Sands has one of the most extensive materials testing laboratories in the world. This lab characterizes materials on Earth so that they can be depended on in space. Over 90% of all the non-metallic materials flown during the Apollo, Skylab, and Shuttle programs have been tested at White Sands. Currently, work focuses on materials proposed for use on the shuttle, its payloads, and space station. Among the unique tests conducted here is the flammability of metals. White Sands is a proven leader in this type of testing and in analyzing how metals burn. Recently, hypervelocity particle launchers have been added to White Sands' arsenal of tools.
Attention all personnel, hazard operations about to commence, 272 area. All personnel not involved, please exit 272 area at this time.
These light gas guns propel objects up to 1 inch in diameter at speeds of nearly 7 kilometers per second, or 10 times as fast as a high-powered rifle. This simulates the impact of meteoroids and orbital debris on hazardous targets, such as pressurized containers, propellant tanks, or other spacecraft components. There is more to the lab area than testing materials or studying explosions. Often, parts that have failed on board the shuttle are analyzed. In the controlled environment of the lab, engineers try to mimic the failures. From that, they can identify the specific problem and work on a solution. Another area of interest is payloads outgassing, or the migration of molecules out of organic products. Tests are conducted on everything from laptop computers to animal enclosures to film for onboard cameras to ensure that nothing toxic is released from materials due to outgassing. Also, payloads that fly together are tested to make sure that one payload's outgassing does not contaminate other payloads. At White Sands, clean rooms are used continuously to precision clean all the parts used in rocket propellant and liquid oxygen tests. These clean rooms are an integral part of the test program. Tests using rocket fuels cannot be conducted without precision clean parts. If a small bit of organic material is on the test article and it is tested in pure oxygen, a fire could result. The clean room not only ensures uncontaminated test results, but more importantly, provides a necessary safety factor. One indispensable and rather unusual test capability is the odor panel. Since 1967, a panel of volunteers has sniffed literally every item that has flown in the crew cabins of NASA's manned spacecraft. This is important because a bad odor permeating an enclosed cabin can become unbearable. It could distract crew members from the business at hand. The odor could even be a catalyst for motion sickness.
Mark, we're getting great pictures down here.
White Sands also provides support for chemical analysis, calibration, valve disassembly and assembly, metallurgy, X-ray, special component level testing, and photography for all propulsion and laboratory activities. Technical support at White Sands doesn't stop with the completion of the test. These engineers, scientists, and technicians are determined to provide the answers to whatever questions might be posed. They have even compiled several handbooks on aerospace fluid hazards, as well as provided support for special investigations and hazard assessments. In addition to providing top-notch test cells and laboratories, the White Sands Test Facility also supports another important part of the shuttle program.
Thank you for your help.
A dry gypsum lake bed at the nearby U.S. Army White Sands Missile Range provides 2 7-mile-long runways for shuttle landing operations and astronaut training.
Airspeed 292.
Designated White Sands Space Harbor, this area of the missile range serves as an alternate landing site for the shuttle. Although only one shuttle has landed here, the Space Harbor is used every day and often at night as an essential training ground for shuttle pilots. Here, astronauts practice approaches and landings using the shuttle training aircraft, which mimics the shuttle's flight characteristics and instrumentation. In 1989, a third runway was added to train astronauts for transatlantic abort landings. This shorter and narrower runway is almost an exact duplicate in size and appearance to the one at Ben Guerir, Morocco. Located near the White Sands Test Facility is another installation which provides an important service to the shuttle program: the Tracking and Data Relay Satellite System ground terminals. 2 terminals are located about 4 miles apart. Each is responsible for receiving voice, television, and data from orbiting shuttles. Both terminals are supervised by NASA's Goddard Space Flight Center and are not related to the White Sands Test Facility. The outstanding track record at White Sands centers around its people. They are involved in all facets of the test, from inception to completion. These professionals have the resources, training, and experience necessary to provide state-of-the-art support for various test requirements. The future holds many challenges for the White Sands Test Facility. At White Sands, years of experience combined with the physical assets of the facility will continue to provide the capability to safely evaluate potential hazards which may arise on Earth and in space. Whether it involves firing rocket engines, evaluating advanced materials, studying explosions, or testing new exotic propellants. Today's work at the White Sands Test Facility will continue to minimize risks for tomorrow's space flights.